Hello everyone, my name is Sharsa Dasmolchi. I'm a PhD candidate and a member of the Berkeley Research Group in the Department of Civil and Environmental Engineering at UCLA. Today, I will present my co-author to introduce our most recent study and journal publication on reliability-based design of force control components in rocking steel braced frames. In this slide, I will give an overview of the proposed reliability-based methodology. The first step is to assume a value for the ratio between the resistance and load factor used in the LRFD-based design. Then, assuming a log normal distribution governs the probabilistic demands and capacities of the braced frame elements, we can use these two equations to compute the reliability index for the force control component and the corresponding probability of demand exceeding the capacity. The next step is to compute the probability of exceeding system-level limit state with and without considering force control component failure. By integrating these two fragilities with an appropriate hazard curve, the limit state exceedance risk, such as the probability of collapse in 50 years with and without consideration given to force control component failure, is obtained. The incremental risk added by the force control component is used as the basis for determining the appropriate load and resistance factor ratio. If the total or added risk is below a predefined threshold, the resistance to load factor ratio is deemed acceptable. Otherwise, the resistance load factor ratio should be decreased and the process is repeated. The reliability-based methodology is applied to 3, 6, and 9-story contour-rocking steel braced frame cases. Two-dimensional nonlinear structural models are developed in OpenSys for the 3 building cases. The key model components include the braced frame elements, which are the force control components and the fuse and PT. The 44 far-field ground motion specified in the FEMA P695 guidelines are used for the analysis. This plot shows the probability of demand exceeding capacity in the force control components as a function of their shaking intensity. For all 3 buildings, the probability of demand exceeding capacity is generally highest in the beams and braces. This table shows the various models that are used to isolate the effect of force control component failure on the system-level performance. The all-elastic model is used to compute the probability of limit state exceedance when force control component failure is not considered. The fragility curve obtained from the all-elastic model is shown in this figure. Generally, the collapse margin ratio is higher for the taller buildings. In order to compute the incremental collapse fragility caused by force control component failure, structural models that consider the nonlinearity in the beam, brace, and columns are used. The figure shows collapse fragility curves for all 3 building cases with and without considering beam, column, and brace failure. For the 3-story case, column failure has the largest effect. For the 9-story building, the overall effect of the force control component failure is negligible. This figure shows the effect of each type of force control component on the 50-year probability of collapse over a range of resistance to load capacity ratios. For 3-story building, column failure has a significant effect on collapse risk. For 6 and 9-story buildings, beam failure has a modest effect on collapse risk at higher resistance to load capacity ratios. Thank you for listening. Please visit our group website to check out more details of our research work.